Good morning, everyone. My name is Ravindra Bhavani Korrapati. I currently pursuing my post-graduation in Vignan's Foundation for Science, Technology and Research in the stream of Computer Science and Engineering. Now I am going to explain about understanding sorting concepts and algorithms. The presentation focuses on what is sorting, why sorting is important, types of sorting, detailed explanation of quicksort. Let us see what is sorting. Sorting is the process of rearranging a collection of items, whether it may be numbers or strings or any other objects in a specific order, typically in ascending or descending order. This fundamental operation is essential for efficient searching, data organization, and problem solving across computer science stream. Let us take an example. This is an unsorted array of elements 72541. After applying any of the sorting techniques, we will get the result in an ascending order like 1, 2, 4, 5, 7. In this way, the sorting helps in real world applications. Why sorting matters? The importance of sorting can be explained with the help of three key points. The first one is fast search operations. The sorted data allows binary search. Search time reduces from the time complexity of big O of n to big O of log n. Means here we can reduce the half of the time. It is very efficient for large data sets. And the second one is data analysis simplified. Here we can find the minimum and maximum values, detect the duplicate elements, calculate median, rank data easily. And the third one is algorithmic foundation. Many advanced algorithms depends on sorted data. We can use it in database indexing, computer graphics, machine learning pre-processing. With the help of these three key points, we can know why sorting matters in real world applications. Types of sorting techniques. There are various sorting algorithms are used in data structures. The following two types of sorting algorithms can be broadly classified. One is comparison based and the other one is non-comparison based. We compare the elements in a comparison based algorithm. We do not compare any of the elements in a non-comparison based sorting algorithms. Now this flowchart helps which sorting algorithms are comes under comparison based, which algorithms are comes under non-comparison based. Bubble sort, insertion sort, selection sort, quick sort, merge sort, heap sort are the algorithms comes under the comparison based, and the count sort, radix sort are comes under the non-comparison based algorithms. Key sorting properties. If we understand these characteristics, we can choose the better sorting techniques for the given statement. First one is stable sorting. When we want to maintain the relative order of equal elements, and the important when sorting records with multiple fields. If this is the situation, we can go with merge sort. Here the merge sort is stable. And the second one is in place operations. If we uses very little extra memory and sorting is done within the same array, so this is the situation we can use selection sort. And the third one is time complexity. Naturally the time complexity means the amount of time required to execute particular problem. So if there are three cases, best case, average case, worst case, so these three cases helps chooses the right algorithm. And the fourth one is adaptive performance. So algorithm performs fast on nearly sorted arrays. So if this is the situation, we can use insertion sort. The insertion sort takes big O of n for nearly sorted arrays. Quick sort. It is the divide and conquer strategy, which means the array is divided into smaller subarrays and the sorting is done recursively. So here we can select the pivot element. Based on the pivot element, we can sort the arrays. So this is the
Quicksort
video.
utilizes a divide and conquer approach. We select a pivot element.
So in this video, we can select the pivot element as the last. Based on the pivot element, we can sort the array. So let us see how we can solve. Why quicksort? Simple sorting algorithms like bubble sort, selection sort, insertion sort. These sorting techniques have taken the big O of n square time complexity, which is inefficient for large datasets. Suppose we can take the quick sort. It can reduces the unnecessary comparisons, perform much faster in practice, preferred when efficiency and scalability are required. In this video, clearly explains how quicksort was solve the problem in the big O of n log n time from big O of n square. How quicksort works. Let us take an example 835269. So by performing quicksort, we can initially choose the pivot element. So there are different ways to can choose the pivot element. We can choose the first element as the pivot, or last element as the pivot, or middle element, or any random element. Suppose I can choose 6 as my pivot element. So the second step is partition. Rearrange the elements in the array such that all the elements smaller than pivot are placed on the left side and all the elements greater than pivot are placed on the right. So if my pivot is 6, then all the elements smaller than pivot comes under left side. 3, 5, 2 are the elements smaller than pivot and the elements larger than pivot are 8, 9 comes under left subarray. So as we all discussed about quicksort is a divide and conquer strategy. So divide means we can divide the array into two subarrays, left subarray and the right subarray. And we can conquer and we can recursively apply the merge sort for left subarray separately and the right subarray separately. Here we can take 3, 5, 2 as the sorted as the array. We can take pivot as 2 and pivot element smaller than pivot comes under left subarray. Here no elements smaller than 2 and largest elements are 3 and 5 comes under the right subarray. Like this we can apply recursively the sorting algorithm. And finally combine. Since quicksort performs sorting in place, no separate merging is required and the array becomes sorted automatically. Partition logic. Here we can see the partition logic with the help of this example. So here I can take my pivot element as 10 and take two pointers, I pointer at lower index and j pointer at high minus 1 index. Here I pointer can move from left to right and the j pointer can move from right to left. So while I less than or equal to j, which means I crosses j until we can run this loop. Here in this loop we can take another loop. Why e of I is less than pivot I plus plus, which means e of I is here 6 and pivot is 10. 6 less than 10, condition true, we can increment I value. And again check 7 less than 10 and condition true, we can increment I value. Here the condition fails, 11 less than 10 not. So we can stop I pointer is at second position and run this loop while e of j greater than pivot. Here 15 is greater than j. 15 is greater than 10 pivot element, so it's true, we can decrease jth pointer. Here 12 is greater than 10. Here the condition true, we can decrease the jth pointer. Here 5 is not greater than 10. Here we can stop and the jth point is at index 3 and check if I less than j. I is at second index and j is at third index, 2 less than 3. The condition true. Swap a of I and a of j means swap 5 and 11. The elements in are 6, 7, here index I and index j, 12, 15 and 10. and the pivot is 10 only. And check the condition I less than j. Yes, ith index is at second position and jth index is at third position, and run again this loop while a of I is less than pivot. 5 is less than pivot, then we can decrement this value I to this. Here the index is 3 and 11 is less than 10. The condition false. We can again run this loop. E of j is greater than pivot. 11 is greater than pivot, and we can decrement it. Here the jth pointer comes to second index. Here this is the second index. And 5 is not less than 10 and the condition false. The jth pointer is here at second index and the ith pointer is third index. We can check this condition I less than j. So 2 is not less than 3, so the condition false, and we can come out of this loop and we can swap a of I and pivot. So a of I is 11 and a of pivot is 10. We can swap these both, and 10 comes here ith position, and a of yes, this 11 comes under this position. So what is pivot? Here the 10 is pivot. The elements less than pivot are comes under left side 6, 7 and 5, and the elements greater than pivot comes under right side 12, 15, and this is the right subarray, this is the left subarray. We can apply recursive to sort the left subarray and the right subarray recursively. So pivot reaches its correct sorted position. When we know pivot reaches the correct sorted position, if the pivot is swapped once, we can fix the pivot element. Check the elements from the left subarray and the right subarray. All the elements under the left subarray are smaller than the pivot, and all the elements greater than the pivot are comes under the right subarray. So this is the partition logic. Let us see the real world problem. An online shopping website displays a list of mobile phones with different prices. A customer wants to sort the phones by price, which means low to higher, to affordable options quickly. So here the list of 6 mobile phones and their prices. Let us see we can apply quick sort, how it can solve. For the quick sort, pivot selection is the initial step. Here we can choose the pivot element as the higher index and take ith pointer as the lower index and jth pointer as the high minus 1 index. Here the ith pointer can move from left to right and jth pointer can move from right to left until the condition was false. So what is the initial condition? While e of I is less than pivot I plus plus, while e of j is greater than pivot j minus minus. Here check the first while condition. E of I is less than pivot. Here the condition false. So ith loop stop here. For check the jth loop. E of j is greater than pivot. Its condition true. We can decrement the jth pointer to this. And again check. And the jth pointer. E of j is greater than pivot. The condition true. Again decrease the jth pointer to this. And again check. E of j is greater than pivot, and again true. We can decrease the jth pointer and check. The E of j is not greater than pivot. Here we can stop the jth loop. After successfully completing the ith pointer loop and jth pointer loop, the ith pointer is at 0th index and the jth pointer is at 1 index. So this is the final ith pointer and jth pointer after successfully completing the loops. Then check ith index and jth index. Ith index is at 0th position and jth index is at first position. Check if I less than j. What we have to do? Swap a of I and a of j. So swap 9 999 to 18,999. So this is what we have done in this. So 9,999 comes at 0th position and 18,999 comes under first position. And we can again check ith loop and jth loop. I increment from 0 to 1 and j increment decrement from 1 to 0. Then check the condition I less than or equal to j. Here I and j are swapped or intercrossed. So we can swap a of I and pivot element. After swapping pivot with the a of I, the pivot are fixed. The pivot comes under the fixed position. So what is the logic? All the elements less than the pivot comes under left subarray, and all the elements which are greater than the pivot element are comes under the right subarray. So we can apply the sorting technique for the left subarray and the right subarray recursively. Here the sorting element from the left subarray is single, so we can't apply. And for the right subarray we have 4 elements, and iteratively take the pivot element as the last index, and the take 0th index as the ith pointer, and take jth pointer as this one. And we can check a of I is greater less than pivot or not. No, here the condition fails. Ith point is a 0 index. Check jth pointer condition. A of j is greater than pivot. That's true. We can decrement the jth pointer. Here again we can check a of j is greater than pivot. Here the condition false. The a of j condition false, and check I less than j. Yes, the condition true. We can swap a of j and a of I. That means 14,999 comes on right position, and which comes under 25,999 comes under jth position. These two values are same. This is ith position and this is jth position. Then check a of I is greater than pivot, so we can increment ith position. A of I is less than the pivot, so the condition false. Ith pointer is at first index, so check the jth pointer. A of j is greater than pivot, true. We can decrement the jth pointer, and again check a of j is greater than pivot, so the condition false. Jth pointer is at index 0 and the ith pointer is at first index. So here the ith pointer and the jth pointer are intercrossed, so we can swap a of I with the pivot element. After applying the quicksort recursively, we can got this is the final sorted array for the mobile phones with the lowest price 9,999 to 32,999. So this is the way quicksort helps to sort the given list of elements. This is the simple logic behind the quicksort. Suppose we can take the highest element as the pivot element, that is last highest index element, and we can take ith pointer and we can take jth pointer. So the ith pointer is we can increment from left to right, and for jth pointer we can decrement from left to right, right to left. So after some iterations the pivot comes to the fixed position, and all the elements less than pivot are comes under the left subarray, and all the elements comes under the greater than pivot element comes under the right subarray. So we can recursively sort the left subarray and the right subarray separately. For the left subarray, again take highest index element as the pivot. 1 comes to the fixed position, and less than 1 comes under the left subarray, and greater than elements are comes under the right subarray. Again sort left subarray and right subarray recursively. Here we can take these are the two elements, we can sort recursively. Like that we can sort right subarray until the single element found, and we can, this is the divide and conquer approach. After dividing we can combine every element in a sorted array. Time complexity and space complexity. The time complexity refers to the amount of time required to execute particular algorithm, and the space complexity refers to the amount of space required to store the particular array elements. Suppose the time complexity best and average case time complexities are n log n. The worst time complexity is big O of n square, which when the pivot selection is poor. So the space complexity is the average case big O of log n and the worst case is big O of n. These are the space and time complexities. Analysis of quicksort by using substitution method. So here is the recurrence relation T of n is equal to 2 into T of n by 2 plus Cn. So by calculating T of n by 2 and put it in the given equation, we can obtain T of n is equal to 4 T of n by 4 plus 2 C of n. And again calculate T of n by 4 and put it in the given equation, we can obtain T of n is equal to 2 into 2 T of n by 4 plus C n by 2 plus Cn. And again we can calculate T of n by 4 and again T of n by 8. By recursively we can calculate at certain number of steps, we can get T of n is equal to T of 1 plus n log n. Here big O of n and big O of n log n. The highest time complexity is big O of n log n. So finally the time complexity of quicksort is big O of n log n. So this is all about quicksort, how the elements are sorted with the help of quicksort. Thank you.